Today we were talking about pressure, pressure at depth, and buoyancy. But first we must define pressure. Pressure is a ratio of force and over the area which it's distributing. So finding an equation for pressure, we know that area, as it increases and the force remains constant, pressure decreases, so therefore area must be in the denominator and force is in the numerator. And you get the equation P equals F over A. So the units for pressure are pascals, and you have force over area equals a Newton over a meter squared, which is 1 Pascal. Pressure is everywhere. It's all around us. In fact, our atmosphere has a pressure of about 101,300 pascals. It's affecting me all the time. So why don't I notice? It's because I was born here and I'm used to it. There's two types of pressure. There's gauge pressure, which is specific to a system, and then absolute pressure, which is gauge pressure plus 1 atmosphere. So for this tire, the gauge pressure would be the PSI of the tire, and the absolute pressure would be that pressure plus 1 atmosphere. Pressure is also felt on all sides. So if an object is completely submerged in a liquid, then the liquid pressure will be felt on all sides, whereas I am in air, I feel the pressure of an atmosphere on all surfaces of my body. Using what we just learned about pressure, what do you think will happen when I lay on this bed of nails? I weigh about 75 kilograms, my back is about a ½ meter by ½ meter square. As you can see, distribution of my force over the area of these nails resulted in me not being penetrated by them. What do you think would happen if I stood on these and reduced the area to the area of my feet?
But what happens when an object is submerged in a liquid? How much extra pressure is added? If a fluid is within a container, then the depth of an object is placed in that fluid can be measured. This is called pressure at depth. The deeper the object, the more pressure is experienced. This is because the force increases as more liquid covers the object. Force is F equals ma, which means your pressure is F over A. To measure pressure at depth is P fluid equals your rho g h. Rho is your density, g is your gravity acceleration, and h is your height at which the object is submerged. Your density is going to be rho equals mass divided by volume. Density can be found of any solid, liquid, or gas by dividing its mass, which is kilograms, by its volume, which is meters cubed. To find your total pressure, you would have to add your P atmosphere with your P fluid, which is just rho g h. Here's the question of the day. Will it sink or will it float? With me, I have an empty bottle can, a filled bottle can, and a really heavy block. Will either of these things sink, float, or do something else? Clearly, the empty can is floating on top of the surface, and clearly, the block is sunk down to the bottom. But this filled bottle can is floating just below the surface. Why is that? Well, we know that the denser an object is, the more it is more likely to sink. We know this because pressure equals rho GH. Rho is your density, and the greater your density, the greater pressure it has, and the more pressure it has, the more likely it will sink.
Why do objects seem lighter and are easier to move in water? This is because there's a force acting upwards on the object. Justin told us that pressure is felt on all surfaces contacted, and Tasia told us that pressure is equal to rho GH. If we think about this logically, the height at the top of the cube, H1, is always going to be less than the height at the bottom of the cube, H2, because the bottom's always going to be deeper than the top. Therefore, the pressure at height 1 is always going to be less than the pressure at height 2. This means there's more pressure here at the bottom, which gives a net force upward on the cube. This is called the buoyant force. Now, to find this using an equation, we know that the net force is equal to the P bottom times the area, because we have to get rid of the meters squared in pascals, minus P top of the area. So that gives you rho GHA minus rho GHA. Rho and G are constant, so we can pull them out, which leaves us with delta H times A. Now this is just your volume. So you have the force, net force, or buoyant force, gives you rho G volume. Now, the volume is not the volume of the cube or the object. It's the volume of the liquid displaced, because this cube, fully submerged, is going to have a different buoyant force than a half submerged cube. Because buoyant force is all about liquid displaced. So when you think of it, think volume. Also, the mass has nothing to do with the buoyant force. A 5 kilogram steel cube is going to have the same buoyant force as a 0.2 kilogram plastic cube, as long as the volume is the same. Okay, so we have a 87 gram cube of aluminum and a 291 gram of copper, and both are 3.2 centimeters on each side, so they have the same volume. So we have our zeroed force sensor here, and we're going to attach the cube to the force sensor. Notice that it's going to give you roughly the force of gravity, so the acceleration times the mass. And as we raise the water and submerge the cube, the force is going to decrease. This is half submerged and it's already decreased. When we fully submerge it, it's going to decrease even more as more liquid is displaced. And this change from not submerged to fully submerged, the change in the force is the buoyant force. We're going to take data, do the same thing with the copper cube, and get back to you. So we took our data, we found the force before we submerged the cube and after, subtracted the two to get our net force, which is our buoyant force. We did the same thing for the copper and averaged the two to get a buoyant force of 0.328 newtons. So that's our experimental. If we plugged it into the equation, F equals rho GV, with our rho being the density of water, 1,000, our G being the acceleration of gravity, which is roughly 10, and our volume of the cube, which would be 0.032 cubed, we get a buoyant force of roughly 0.328, which is the exact same as our experimental, so that worked out perfectly. This just reinforces the fact that buoyancy is all about volume and not mass.